Am I audible? Okay, thank you, Gargi. Thank you. We'll continue with the Exergy of closed system discussion. And let me just revise in a moment what we had discussed in the last lecture. And we would solve one numerical based on this concept. And if time permits, I would take another concept which is called the second law efficiency. So this is a plan. Okay. Let me share the screen. Okay. So as you see on the screen, okay, I will be sort of revising the concepts which we had discussed in the last lecture. What we had discussed in the last lecture was the calculation of available energy of a closed system. So what we had taken, we had considered a closed system in the form of piston cylinder arrangement without walls, and we had considered that there is a gas in it which is at a pressure P1, volume V1, and temperature T1. The pressure and temperature being different from the dead state temperature. And because the system is not in thermodynamic equilibrium with the surroundings, so it has got certain potential to do work. Also, because the temperature is different, there is a possibility of heat transfer if the system is not insulated. So we have considered an uninsulated closed system. So this closed system can interact with the surroundings via the heat transfer and via the work transfer. So in order to calculate the exergy or available energy of the closed system, what we did was we had considered the heat transfer phenomena and the work transfer phenomena separately. Okay. And then what we did was we calculated the exergy of the corresponding heat transfer and the exergy of the corresponding boundary work. Okay. The exergy of the heat transfer, in order to calculate that, I had taken a Carnot engine. Okay, I had taken a Carnot engine operating between the dead state temperature and the closed system temperature, and I had arrived at the work output of this Carnot engine. So the work output of this Carnot engine for some elemental heat transfer del Q, that work transfer expression is equal to del Q plus T naught ds. How do you get this expression? You get this expression by applying the second law expression, that is del Q by T1 is equal to del Q naught by T naught. Okay, and by using the energy balance for a heat engine. So energy balance for a Carnot engine is del Wc is equal to del Q minus del Q naught. Okay, and substituting the value of del Q naught as T naught into minus del Q by T, we get the expression for the Carnot work output, which is nothing but the exergy when an elemental heat transfer was considered. Okay, so this is one expression which we considered, which is to consider the exergy potential, the work potential of the heat transfer, which is happening via the closed system. Then we said that we need to understand that the closed system interacts with the surrounding also by the work transfer, and because if it is a closed system, you cannot have flow work, it would be only the boundary work. Okay, but the boundary work expression would not be should not be confused with the useful boundary work, because what would contribute to the exergy or the actual work potential is the useful boundary work. And for calculating the useful boundary work from the boundary work, we need to subtract the work which is consumed for overcoming the resistance from the surrounding, which is given by P naught dV. So we consider the useful boundary work, that is dWB is equal to dWB useful is equal to dWB minus P naught dV. Okay, so this is another expression, and then what we did was we summed up the two for calculating the total work potential. Okay, so the total work potential is del WC plus del WB. Okay, once you get the total work potential, okay, you substitute these values of del WC and del WB, and you get this expression, that is del Q plus T naught ds minus del Q minus du minus P naught d. Okay, of which this del Q term would cancel out, and you will be left with this expression, that is del W is equal to minus du plus T naught ds minus du plus T naught ds minus P naught dv minus P naught dv. Okay, now allow me to rub this and arrive at the final expression. So I'm erasing this. Just a minute. That has to be integrated, okay, for the overall calculation of available energy, and that integration has to be done between the two states, that is the state of the closed system initially, and finally the end state, that is the dead state. Okay, the final state is the end state, that is the dead state. Okay, so this expression I have now integrated. Which expression? The expression which I have written in the box. So let me just rewrite this. So this del W expression I would be integrating between the initial state, that is state 1, and the dead state, that is not. So this would give me the available energy. Okay, this will give me the available energy. So this would be integral of minus du. Okay, look at this expression in the box. Okay, look at this expression in the box. So I'm integrating this from the initial state 1 to the dead state naught, plus T naught is outside because it is constant. The dead state temperature is not going to change from 1 to 0, or dead state ds, minus P naught is again constant. So integrating it from 1 to 0 dV. Okay, so this is minus U naught minus U1 plus T naught S naught minus S1 minus P naught minus V1. Okay, so what is this? This is an expression for available energy. So I'll just rewrite this in the form which we generally use. Okay, so that expression is now, I'm rewriting this. U1 minus U0 plus V0 V1 minus V0. Look at the sign which I have changed. Okay, I'm just changing the sign of the bracket. S naught, S1 minus S naught. Okay. So this is called as the available energy of the closed system. Available energy of the closed system. Okay. I hope this is clear to you. Is this clear? This derivation? Availability of the closed system derivation, is this clear? Is this clear, this expression? Viraj, Gargi? Okay, Kunal is saying yes. Okay, so you need to practice this derivation. Actually, it is not a difficult derivation, but you might forget some steps. Okay, so the alternative is you just practice it. Okay, conceptually you must have followed. I hope all of you that what exactly we have done. Okay, as I had discussed in the last lecture, we need to. There are two different things. One is derivation. As I told you, that derivation can be done just by memorizing the steps without understanding the concept. And second is the conceptual part. Okay. So whether the conceptual part is clear, the derivation you can anyway learn. I hope it is clear conceptually also. What exactly we have done, Kunal? Whether conceptually it is clear to you all, this derivation? Okay. If it is clear, then let me just write few more steps and few more terminologies which you might come across. So let me just erase this one first. I'm erasing this useful boundary word. Now, suppose you are taking this, if you want to calculate the change in availability, okay, change in availability. So suppose this is availability. And suppose initially the state was at A1, okay, sorry, state was at some state 1. So the corresponding expression you will get is A1, okay. And let us say finally, suppose after some time, the system reaches the state 2. So in that case, when the system reaches the state 2, the corresponding expression for availability would be U2 minus U0 plus V0, V2 minus V0 minus T0, S2 minus S0. Okay. And then you can figure it out that if I want to find the change in availability during some process 1 to 2, okay, if you want to find the change in availability during some process 1 to 2, then that expression would be A1 minus A2. A1 minus A2. Okay, so this way, and if you write it as A1 minus A2, you understand that it becomes like this expression U1 minus U2 plus V0 V1 minus V2 minus T0 S1 minus S, like this. Okay, so this is just rearranging the things. So what we get from this expression which is written in the bracket, it tells you the availability Now, Kunal, am I audible? Kunal, Dheeraj, am I audible? Gargi? Okay, thank you, Vedant. So the question, thank you, Kunal. Find the availability of a gas during a non-flow process when when the when the system is at a pressure of 8 bar and the temperature is equal to the dead state temperature, which is given to be 288, temperature is the same, and you are given that R is equal to 0.287 kilojoules per kg Kelvin. Okay. To solve this, so what is the expression? We will use the availability expression. So availability is U minus V naught or U1 minus V naught. So I am considering the initial state as U and final state as Z state plus P naught V minus V naught minus T naught S minus S naught. Okay, S minus S naught. So what you need to find is you need to find U minus V naught. How to find U minus U naught? You can find U minus U naught as CV delta T. That is T minus T naught, and obviously this would be 0. Why it would be 0? Because the temperature is the same. Okay. If the temperature difference is 0, T is equal to T naught. So the first term becomes 0. How to find P naught V minus V naught? So we need to use the gas law that V is equal to RT upon P per unit mass. Okay, RT upon P. Okay. So substituting it this way, so what you'll get is this would be P naught RT upon P minus RT naught upon P naught. So this will give you the second expression, and the third expression is the entropy change. For an isothermal process. The process is isothermal. Okay, so for the entropy change, that is S naught minus S1 is equal to what it would be? It would be del Q by T. Okay, del Q by T, and for isothermal process, it would be, you need to substitute the appropriate expression. What is that expression? It would be the general expression, it is R log to the base E P by P naught plus Cp ln T naught by T. I hope you have these expressions for entropy change. We had discussed some expressions for entropy change, right? This entropy change expressions, you need to be very comfortable with. If you remember our derivations for entropy change, you can always derive these expressions for entropy change of gases for different processes, okay, and calculate those using the gas laws. Okay, so this is one expression you can use. There are a number of expressions. So depending upon the data, one can use those expressions and just calculate and tell me what is the entropy change. Calculate and tell me what is the entropy change. The unit would be, because it is per unit mass, kilojoules per kg Kelvin. So calculate this, substitute this values. The CP is 1.005. This T naught and T, they are same. Pressure is 8 bar, and P naught pressure you can take it as atmospheric pressure 1.103 bar, and R value you can take it as 0.287. So calculate and tell me what is the entropy change. Just calculate and tell me the answer. Shubham Ande. हाँ बोल काय पाठवू ब्ल्यू म्हणजे कुठला अच्छा अच्छा पाठवतो हो हो ठीक आहे पाठवतो Yeah, Neha, you are right. Neha has got the answer. Anybody else who has got the answer? Neha, you are right. Aditya, Kamlesh, what have you calculated? Kamlesh, you are wrong. Kamlesh, check your answer. Kamlesh Sonone. Okay, once you Kamlesh, check your answer. Okay. Jay, you are right. Okay, so most of you are getting it right. So let me write down that answer as point 0.593 0.593 kilojoules per kg Kelvin. Okay. So you should get this answer as close answer. And now, once you get this answer, you can find now the available energy. Okay, for available energy, so 0.593 you need to substitute over here. So this would be substituted. Okay, so this would be S minus S naught. S naught minus S1 you have calculated. So this would be minus 0.593. You just check whether I am correct. And this is 288. This is 288. Okay, and this is C. This is 1 point. This is okay. What is P naught? V minus V naught. V naught V minus V naught. This R would be. Let me just rewrite this expression. Put these values and just tell me the final answer. Okay. Put these values and tell me the final answer of available energy. So if I put this P naught is how much? P naught is, you need to be careful with the units, please note. P naught is 1.13 bar. So 1 bar is 100 kilopascals. 1 bar is 100 kilopascals. Okay. So because you are expressing everything in kilos, so I need to multiply this 1.013 with 100. Okay. R is 0.87. R is 0.87. P again, P is in bars. So this again I will have to put it as 8 into 100 kilopascals, and P naught is again 100 kilopascals. Okay, so just be careful while substituting the units. Okay, be careful while substituting the units so that you get the final answer in kilojoules per kg. Your answer of available energy would be in kilojoules per kg. Please note that I am repeating that the pressure which you are substituting has to be in kilopascals. It has to be in kilopascals. The value of R, the gas constant, has to be in kilojoules per kg Kelvin, and the temperature in Kelvin, Okay, temperature in Kelvin. So this T is 288. This T naught is also 288. Okay. So just tell me what is the answer you are getting finally. Tell me the final value of A. Final value of A. Okay, what is the answer you are getting? Kunal is getting 242. Kamlesh is getting 0.73. See, the answer with me is around 98. I just want to check. Yeah, Jay is getting 98.59. So Jay has got it right. Jay has got it right. The answer with me, just check your answers. The answer with me is 98.59. Okay. So let me just check the available energy. I'm using a small a because I'm writing it as capital A upon M. That is available energy per unit mass. That value, after substituting, I have 98.59 kilojoules per kg. So Jay has got it correct. Others, they need to just check whether they're also getting it right. Whether they are also getting it right. Okay. It's a matter of substituting the value in something else. So as you see, what happens is this kind of numericals, they get reduced to two different things. One is you need to be comfortable with the entropy change calculations of gases. Okay. In the exam, if you are asked to calculate the availability of a gas, then ultimately what you are required to calculate is you need to just apply the gas laws first, and you need to calculate the entropy. Yeah, Aditya, you have also got it right. Entropy change expressions. Now, entropy change expressions, we have already done those kind of expressions when we talked about entropy as a property, and we talked about the entropy change of the ideal gases. So you need to be very much comfortable with this kind of calculations of entropy change of gases. And if you are comfortable with that, then it is simply a matter of substituting those values in the expression which we had derived. Okay, so the expression which we had derived is u minus u naught plus p naught, b minus v naught minus t naught, s minus s naught. Okay, so this expression would give you the availability of gas, right? So such kind of numericals, uh, uh, which are for calculation of availability, would require you two things. One is you need to be competent in handling the numericals involving properties of gases, the gas law especially, right? You must be comfortable with the different processes, and you must be comfortable with the numericals of various type involving entropy change of gases. So different types of processes. So for example, this process which was considered, okay, here you see that this is an isothermal process. So the non-flow process which we considered is an isothermal process, right? Similarly, one can consider, let us say, I will take a same numerical with some different value. Let me take this second numerical, wherein your dead state remains the same. That is, dead state is, let us say, P naught is 1.103 bar, and the dead state temperature is 288 Kelvin, 288 Kelvin. And now it is given that the closed system, which we are talking about, this closed system is having a pressure of, this closed system is having a pressure of 8 bar, 8 bar, and the temperature is 400 Kelvin, 400 Kelvin, right? So in this case now, you will have the exergy because of both what? Can anybody answer? In this case, you will have exergy because of both the things. Which two things you will have exergy because of which two things? Can anybody answer this conceptually? If you are having the given data, you would have exergy because of what? Aditya, Gargi, Kamlesh, Kunal. Anybody? You would have exergy because of which two things? One is, yeah, anybody? All right, maybe you're not able to answer. Whatever. One is the exergy because of the heat transfer, and other is the exergy because of the useful boundary work. Useful boundary work. Okay. Why would that be useful boundary work? There would be useful boundary work because of the pressure difference. Because this pressure and this pressure is different. Okay. So you will have some boundary work. You will have some boundary work. Second thing is, because there is a temperature difference. In the earlier problem, there was no temperature difference. So because there is a temperature difference, so you would have heat transfer and the corresponding exergy, right? Actually, the heat transfer here is from 400 Kelvin and finally up to the dead state. Finally up to the dead state, that is 288 Kelvin. So because both these factors, that is both the heat transfer from the closed system and the work transfer from the closed system is going to contribute to the exergy. Okay. So again you can calculate this by using this expression. A is equal to u minus u naught plus p naught RT by P minus are T naught by P naught. Okay, that is V minus V naught. This is V minus V naught minus T naught. Yes minus yes naught. Yes minus yes naught. Okay, so you again calculate yes minus yes naught. Okay, and then that s minus s naught will get a negative value. That s minus s naught will get a negative value. You can put it over here, and that will give you the finally you will get the bit transfer. Okay, so s minus s naught you can calculate whatever way you do it. So let me just calculate the entropy change. In this case, what would be the entropy change? Can anybody tell me the value of entropy change in the second problem? Can anybody tell me the entropy change value in the second problem? Again, the same expression has to be used for entropy change, which is what R. Suppose I am calculating S naught minus S instead of S minus S naught. Okay, so it would be R ln P by P naught plus Cp ln T naught by T naught by T. Okay, or if you are substituting S minus S naught, then just reverse the same. Reverse the case. Okay, so that value S naught minus S naught minus S. Anybody has calculated S naught minus S? Calculate S naught minus S and let me know the answer. And then put the value of S minus S naught as negative. Nobody is getting this? Or you are not able to communicate with me? Yeah, Jay is getting it. So Jay has got, Jay, just check your answer. And the answer with me is different. So Jay, you need to check your answer. What is R? R is 0.287. Okay, in this case, T is 400 Kelvin and T naught is 288. And the Cp value of gas, if it is not given, you must know that it is 1.005. The Cp value of gas, it is 1.005. Okay. Neha, just check. You have some different answer. Neha, Cp is 1.005. Cp value is 1.005. Pressure is given to be 8 bar. Pressure is given to be 8 bar. And this is 1. Just let me know what is the answer. Some answers some students are giving. Maybe I have some incorrect answers with me, but I just write down. Just check whether my answer is correct or you. I have not solved it on my own, so I'm not sure about the calculations. But you just tell me. I'm just putting some values. Okay, just tell me whether this answers 2.87 log to the base e 8 upon 1.013 plus Cp, which is 1.005 log to the base e 400 upon 288. So what is this answer, Kural? Is it 0.26, Kunal? 0.238. Neha is saying 0.238. So maybe you are right. Maybe my answers are wrong. Okay. So if all of you are getting the same answer which Neha is giving me, we'll take that value for our calculations. Okay. If all of you are getting the same answers which Neha is giving me, then maybe I will take the your values. Uh, whether the answer is 0.238, Neha, and others, I did. Now she is writing 0.26. Aditya, Gargi, Kamlesh. It is logged with the base E. Okay, please note that. So I don't know. Let us say that it is 0.26 and go ahead. So I'll just put it as 0.26. I don't know. And then if it is 0.26, okay, then S1 minus S0 is minus 0.26. Okay, and that value you need to put it in your calculation of available energy. That value you need to put in your available energy expression. That is, you will be putting this value. See, it is T2 by T1, no? So it is T2 is 400 by 288. Jay, you should not take it as 288 by 4. It is T2 by T1, no? T2 by T0. T2 by T1. Final is T2. T2 is not. Okay, so it is 288 by 400. Okay, right. So just a minute. One mistake is being made over here. That is, you need to be clear that the expression involves calculations of end state upon the initial state. So P, okay, here it is. See what I am writing it is as, here it is P or P1 or whatever P, and here it is P0. So this is P T0. Are you getting it? So it is T upon T0. It is T upon T0 and not T0 upon P. So Jai, is this clear? So just do this correction, Jay, and tell me the answer now. So Jay is using 288 by 400. It has to be 400 by 288. 400 by 288. Right. Now it is right. Okay. So now it is consistent with my calculations. So now it is 0.923. So we have found out the mistake. So the mistake was in arriving at this value of logging T1 by T0. So please make this correction and please write this expression of entropy change. The value of entropy change as 0.923 and S1 minus S0 would be, because it is the entropy of the system would decrease, so it is minus 0.923. So this is negative. So when you put this negative sign in the expression of availability, so the availability expression is availability expression is U minus U naught plus P naught V minus V naught minus T naught S minus S naught, and this I have written it as, because internal energy is CVDT, so CV T minus T naught, CV T minus T naught plus P naught into, instead of V, I am writing it as RT by P minus RT naught by P naught. See, I'm just applying the gas law, nothing else. Okay, minus T naught. Yes means S1 minus S naught. Okay, so this value is minus 0.923. This T naught is 288. P naught is 288. P naught is 1.013 into 100 kilopascals, and similarly this pressure values are to be taken in kilopascals, and the R value has to be taken in kilojoules per kg Kelvin. CV is 0.717 or 0.717 is the value of CV, right? So from which you will get some value of availability. So calculate and tell me this value. I have substituted the values. T, you know, the value of temperature is 400 Kelvin. This is 400. T naught, you know, it is 288. Other things I have written on the board. Okay. So please note that the value of entropy change, yes, S1 minus S naught, or whatever you want to write, yes, or S1. If you are comfortable with 1, I'll put it 1. Okay, so this S1 minus S naught has to be minus 0.923 because the entropy of decrease of the closed system. So just tell me the value of availability of the ideal gas during a non-flow process when the initial state is pressure is 8 bar and temperature is 400 Kelvin. Okay, so Jay has got the answer right, and the answer is, let others also answer. So the answer is 278. The answer is 278 kilojoules per kg Kelvin. 278 kilojoules per kg Kelvin. Okay. So just I want to tell you that solving this is not very interesting. You need to remember the steps and you need to be careful with the units. Okay. In spite of understanding the concepts, there is a possibility that you make some mistakes in substituting the values, especially the units of pressure, the units of R. You need to substitute everything in consistent units. Okay. For example, here I am substituting the pressure value in kilopascals. The reason is because I am taking the value of the gas constant R as 0.287 kilojoules per kg Kelvin. If I was using the value of R in joules per kg Kelvin, then the values of pressure I would have taken it in pascals. Okay, Newton per meter square. So these things you should understand. So here I have consistently used the kilo units. I am writing kilo units everywhere. So CV value, also the CV units, this unit of specific heat at constant volume is 0.717 kilojoules per kg Kelvin. Okay, earlier when we talked about CP value, which was 1.005, the unit of that was kilojoules per kg Kelvin. So you should be very careful when solving these numericals about the units which you are substituting. Else, in spite of writing the expressions correctly, you might end up in the wrong answers. Okay. So this way it is not that this is the only way, but this way one can calculate the exergy or availability of the closed system. Okay, closed system is the non-flow system. And as I told you that solving this numericals would require some practice, clarity about the units, and clarity about the concepts of ideal gases, nothing else. Otherwise, it is very simple. Okay, it won't take much time to solve this. So you need to remember this expression. Please note, you need to remember this expression for availability of a closed system whenever the derivation is asked or the numerical is asked. Okay, with this, I plan to end this today's session. Okay, in the next class, I would take another interesting concept, which is the exergy of the steady flow system, and the last concept, which is called as the second law efficiency. Okay, so with these two concepts, we would be ending this chapter on available energy or exergy. I hope that you are enjoying these sessions on Exergy. This is a bit more demanding, I understand, but the advice is, again, as I said, if you are getting a bit panicky about understanding this, you need to go and visit the videos which have been uploaded to you, uploaded for your benefit, and also solve as many problems as possible and the derivations. So here, the scope of this Exergy is you would be asked some derivations, you would be asked some numericals, and that's it, right? So thanks for joining for the today's session. Have a good day.